greatly reduced audience. Um, now, so if any of you have been keeping up with all the news about the coronavirus, one of the news stories was that my graduate alma mater, Stanford, they, in a sense, closed their campus down because they had one case, a faculty member in their medical school came down with a virus and possibly a couple students too. So they immediately shifted to have all of their classes just move to online. They're in a quarter system. They have 2 weeks left in the quarter. So no classes can meet on campus or exams. Exams would have to be done in a take-home format. And so that had me thinking, like, should I be prepared for the same kind of thing happening here? Because I'm not aware of cases in Mississippi.
They just confirmed one in Jefferson Parish, Louisiana.
Okay, yeah, and
close.
Oh, really?
They never reported it. It was one of the nursing school professor's daughters.
I wonder if it was never CDC confirmed.
I don't know. I remember hearing about that, but I've never heard it ever get confirmed. I thought it was just hysteria.
It's super sketch, though. I mean, Mississippi might just try to keep that stuff under wraps. Like, don't want to talk about it. But it happened.
Yeah. So.
And we're mostly all poor, so we don't travel. So.
Yeah, and people don't want to come here. So.
Yeah,
we might be one of the least affected places in the country.
If it's in Louisiana, then that means it's close enough. But I've been hearing a lot of my teachers who were like the English professors, like they were supposed to be going to all these different conferences this semester, and like every one of them has been shut down. Like they're not going to St. Louis for this thing. Mm-hmm. Another one was supposed to go to California. That one got cut off real quick.
Yeah, well, yeah. California's been pretty badly affected. Yeah, I was supposed to be going to Auburn this coming weekend, and that got pushed back to fall. I have another one in Missouri, but I'm still waiting for word on. I have 3 more conferences in the coming months after that, and I'm just waiting for them. I just wish they'd make up their mind, so I know what's going on. But I feel like if that happens, like we have a case at USM or something, like during the semester, I feel like this class would be particularly well equipped in the case of adjustments, because I would just keep recording my screen and talking just with nobody here, and I guess I'd be doing it from home, and posting videos for you guys, and you guys are emailing me your homework anyway, so you would keep doing that, and then for the final, there's the option of there's a MATLAB assignment, and the oral final exam. And usually most choose the latter. And I guess if it came down to it, the oral could be administered over Skype or similar technology. Which I actually have done before for non-virus situations. So I feel like it wouldn't affect us very much, but I don't relish the idea of giving my Math 285 students take-home tests. So, so this is going to be interesting to say the least. So, I guess all we can do is just keep an eye on what the university decides. The university's already named, I guess you call it a coronavirus czar. Someone who's going to make the call as to how we respond as an institution. So,
They haven't said anything about it.
The only thing that's been handed any official edicts is that the university will not approve travel to the most affected countries, which is right now is just China, South Korea, Italy, and Iran. So would have like a level 3 CDC warning, but that's just it. That's something we need to pay attention to. Is as I think certain other countries, like France and Spain, are having a growing number of cases. Yeah, I would not want to be traveling to California right now as much as I love it there because
I wouldn't even get on. I wouldn't even go to the airport right now. Even go into
yeah,
Florida.
hmm
I wouldn't get on. I wouldn't even go into the airport.
yeah,
I feel like that's very Mississippi.
yeah, and I'm glad that I don't have any flight plans for until June. Um, but dang it, I tripped to New York and bought Broadway tickets, so that hopefully things have stabilized by then. But yeah,
I mean, I know the university sent an email, kind of precautionary, talking about what
Yeah.
you should or shouldn't do,
yeah,
this, that, or the other. But like, it's bad, I guess. But like, is it any worse than the flu?
well,
I mean, I know it's growing exponentially in comparison to the flu, but
in terms of
not-
number of cases,
yeah, number of
yeah,
cases
apparently its transmissibility
is much.
is much greater. Like I guess the virus lasts longer outside the body. But as far as actual symptoms, if you are otherwise healthy, it seems to have very little effect. But yeah, it does feel like the flu, or some people catch no symptoms. They don't even know they have it, and then they pass it on to how many other people while they felt fine. Apparently, if it gets to your lungs, then you're in serious trouble. That's where the fatalities occur. But yeah, like it seems to have very little effect on children, which is thankfully, but also quite unusual because most of these conditions like these, it's babies and the elderly who are at most at risk. So it's an unusual one. So scary times we live in. Okay. But yeah, so if something happens that shuts us down as a campus, then well, I guess we'll be told about how we're supposed to proceed, and we'll just try to keep things going in some way. All right. This advisory still applies. Oh, I haven't put anything on the screen yet. Well, I haven't done anything on my screen either, except yak. So let's get this up there. There. Okay. So this advisory still applies. I still do not have a critical mass on homework 2. When I do, so I may be doing. I'll certainly be doing some grading over spring break. Okay, so
Are you talking about homework 3
right
right there?
here,
Yeah.
any homework whatsoever. Well, let's take a look.
Homework 3 is due on Wednesday or Thursday.
Oops, that's the wrong site. Homework 4 is. Okay. So, well, I mean, everybody's in the same boat. I don't think anyone has submitted homework 3. And less than half a class, oh, I think close to half a class has submitted homework 2. So, well, no, that's what break is for, I guess, to catch up on stuff. Not for anybody having fun, students or faculty.
We're not going anywhere now.
Well, yeah, there you go. Yeah,
Can't go nowhere.
yeah. Okay. Now, so last time I was going over fixed point iteration, and so I'm going to continue with that and a segue into Newton's method and the secant method, which will be review for those of you who took 460, 560 last semester, and those who did not, you'll be brought up to speed for stuff that is new to everybody that I'll be covering on Wednesday. So, as a quick recap on fixed point iteration, Okay. Iteration for x, solving x equals g of x. That is just computing each new iterate by substituting the previous iterate into function g. Has a solution, a numerative existence of a solution, if, or has a solution on a given interval AB, if function g maps AB into AB. So in other words, you pick x in AB, plug it into g, the value that you get is also in AB. Solution is unique if the derivative in absolute value is less than or equal to some constant L that is less than 1 on AB. All right, so that's something we could use for this next topic that I have here for relaxation. So to use fixed point iteration to solve an equation of this form, f of x equals 0, we can instead solve x equals g of x, where g is defined as follows. G of x is just equal to x minus lambda f of x. Okay. Yeah, just got a news alert that the whole country of Italy is locked down. I know it's one of the countries that has it worst. Where the constant lambda is non-zero. Okay. So that way, so g of x equals x if and only if f of x equals 0. So the two equations are equivalent. So how can we choose lambda to speed up convergence? The goal is to minimize the derivative. Because the derivative, we want it to be bounded away from 1. So the smaller the derivative is, the faster convergence will be. Okay. So here's how we'll proceed in doing that. And the result will be a much faster method. So the assumption I'm going to make is that f prime at the root. Okay, so I'm solving. So x star is the solution. So we're going to assume that okay, it's some value alpha which is positive. Okay, make sure I have the right notes here. Okay, actually I'm going to call this something else for consistency of the book. All right, so m star is like the slope of f at the root, and we'll assume it's positive. Okay. And f prime is continuous at the root. Now, why that is important is if it's continuous at that point, and it's positive at that point, then I can say that there's an interval around the root such that f prime is positive in this whole interval. So that's a very important aspect of continuity, it's actually useful in quite a few proofs. That if a function is strictly positive at a point and continuous there, then because of continuity, it has to be positive near that point. Now, you probably can't go very far away from x star and still have it be positive, like if this is a small positive value. But at least you know that there's some interval on which it remains positive. Okay. So since it's positive f prime on this whole interval, then I'm going to add some more notation here. Okay. That f prime is bounded below by little m, bounded above by big M. Because a continuous function on a compact set, and by compact set in this case I mean a closed interval, is guaranteed to have a min and a max. And so little m and big M are those min and max. Okay. All right. Now, okay. Oh, I should say on this interval. Stupid thing. So this interval is x minus x star less or equal to delta. So this same interval right here. So delta is serving as a radius, if you will, and x star is the center. Okay. That these bounds, little m and big M, those are positive. Because we already know that f prime is positive on this whole interval. Okay. Now, oh, hey.
I'm
Oh,
a good student. I came back.
are you finished or just?
I did finish.
Okay. Well, there's one. Okay.
I came back.
Alrighty. So now that we have f prime sandwiched between these two values, what about g prime? Well, g prime is equal to 1 minus lambda f prime. Now, f prime at this point, or sorry, lambda at this point is unknown. Okay. So we have a following. Because f prime is subtracted here, we have g prime of x is less than or equal to 1 minus lambda little m. And it is greater than or equal to 1 minus lambda big M. Okay. And I'm going to name this interval that I have. I'm going to call it I, just for convenience. So that's the interval that I have here. And here. Oh. Okay. All right. So we know that g prime is sandwiched between these two values. We also know that we want it to be as small as possible. So bounded by some constant that's less than 1. So since we're free to choose lambda, how should we choose it? Okay. And keep in mind that lambda has to be non-zero. Now, so to make it as small as possible, here's what I'll do. We set the following. This bound here 1 minus lambda m, little m, equal to L. And then 1 minus lambda big M is equal to minus L. Okay. So if we set these bounds to be negatives of each other, then the absolute value of G prime will be less than or equal to L. And hopefully it will also be less than 1. Okay. So I don't know what lambda is, I don't know what L is, but I'm going to use these equations to figure something out here. So what I'm going to do is I'm going to set these equal to negative each other. So we have 1 minus lambda little m is equal to negative of 1 minus lambda big M. So that's going to be lambda m big M minus 1. So now what I can do is just rearranging this. I'm going to move this minus 1 to the other side, and I'm going to move this lambda little m to the other side. So now I can solve for lambda. It's 2 over big M plus little m. Okay, so using this value of lambda in the formula for G, and therefore G prime, will get me G prime bounded by values that are negatives of each other. So now what I'll do is I'm going to substitute this back up in here to find the value of L. So L, which is equal to 1 minus lambda little m, which is equal to 1 minus 2 over big M plus little m, m. So if I put everything over a common denominator, I'm going to get m plus big M plus little m over itself minus 2 little m over big M plus little m. And I simplify that, and I get big M minus little m over big M plus little m. So this is the upper bound on the first derivative, on G prime. Now big M is the larger, so this is positive. But what we also have is, because we're subtracting two positive numbers up top, and this is larger, and then this is, we're adding them down below, we know that it has to be less than 1. Okay. So that's what we want. We want a Lipschitz constant that is, or bound on a derivative, that we know is less than 1. Okay. All right. So this bodes well for fixed point iteration with this G actually working well, if we choose the initial guess that is close enough, at least, because the initial guess ought to be within this interval. And for all we know, that interval might be pretty small. But at least we have some assurance that if we do choose the initial guess to be close enough to the root, that fixed point iteration with this lambda will converge. Okay. But there's one thing I have to be taken care of. Still need to establish the existence of a fixed point. And what that means is, if x is in the interval I, we need g of x also in I. That assures existence of a fixed point in this interval I. So what we know is if we're allowed to assume that x minus x star is less than or equal to delta. So in other words, x is in the interval. So we need to show that g of x minus x star is also less than or equal to delta. So then we know that g of x would also be in this interval. Okay. Okay. So how can we... all right. So what we have is g of x is equal to x minus 2 over m plus m. That's our value of lambda, f of x. Okay. Okay. Now, let's see. Now, what I can show here, okay, this will take me onto a new page. If I look at g of x minus g of y, sorry, g of x minus g of y. So that would be equal to x minus y plus lambda f of x minus f of y. Okay. Wait. Sorry, I think hold on. Sorry, I'm taking the wrong approach here. Scratch that. Okay. G of x minus x star. That is equal to g of x minus g of x star. Because x star is a fixed point, so it's a solution of x equals g of x. But that is equal to g prime at some unknown value c times x minus x star. So this is by the mean value theorem. Okay. Now, g prime, now this unknown point c, okay, because c is in the interval, c is a point between x and x star, therefore it's in the interval, then g prime, we know, is less than or equal to L. And x minus x star, we know that that's less than or equal to delta. But delta is less than 1. No. L. L is less than 1. So because g of x minus x star is less than delta, g of x is in the interval, and a fixed point exists. Okay. So because G is known to map I into itself, so it satisfies that assumption of the fixed point theorem, and because the derivative is less or equal to L, and L is less than 1, we have a following. We can apply the fixed point theorem include that fixed point iteration on x equals g of x will converge for any initial guess in this interval. So we can use this g to solve f of x equals 0. So under these assumptions, it works. But now, if we take a closer look at what the value of lambda is, lambda is equal to 2 over m plus little m plus big M. But what are little m and big M? Those are values of f prime at 2 unknown points. In the interval. Now, by the intermediate value theorem, there exists a point between C1 and C2. So this is due to the continuity of f prime. So there exists a point between C1 and C2 such that f prime. Okay, I'll name this point. I'll call it. I'll just call it C. Stupid thing. Such that f prime of C is equal to f prime of C1 plus f prime of C2 over 2. In other words, so anytime, if you have a continuous function on the interval, you can use your intermediate value theorem to say that that function is equal to the average of the values at the endpoints. So the intermediate value theorem gives you that. So now we have the following. G of x is equal to x minus lambda, which is now known to be equal to 1 over f prime of c times f of x, where c is some point in the interval I. Or x star minus c is less than or equal to delta. Okay. Now, so what we can do is, as xk converges to the root, so this interval, we could use a smaller and smaller interval because we only need some interval on which the derivative of f is known to be positive. So we can use as small an interval as we like. So we can use lambda equal to not just 1 over f prime at unknown point, but 1 over f prime at xk to obtain this iteration. xk plus 1 is equal to xk minus f at xk, and then the denominator will have f prime at xk. And if we look at the value of L, which is how big a derivative gets, as the interval shrinks, then these values of max and min are getting closer together. In other words, L is going to 0. So as convergence occurs, I can shrink. Therefore, L is going to 0. That's because you're taking a max and min on a smaller interval. So thus convergence is quadratic. Okay. So this method is Newton's method for finding a root of f of x equals 0. So you can see how it's based on fixed point iteration with g that's chosen in such a way as to make convergence as fast as possible. So we see the relationship between the two methods where we're using g of this form. Now, any g of this form where we choose some constant, lambda, that's actually called relaxation. But now if we use relaxation with a varying parameter, we let lambda vary from iteration to iteration. And that's what's done down here, to use lambda being 1 over f prime of xk for each k. Then we get even more rapid convergence than the linear convergence that we can expect from ordinary fixed point iteration. But that's just one way to understand Newton's method. Newton's method can be obtained by approximating f of x at xk by the tangent line to f of x at xk. So what happens in that case is xk plus 1 is the x-intercept of the tangent line. So that leads to this same formula here. All right. Okay. So the idea is, at each point you approximate f by a tangent line. Tangent line, it's a linear function, has a unique root that's easy to get. So then we update to get the x-intercept. Then we take a tangent line at the next point and find the next x-intercept, and we obtain convergence. So Newton's method can be shown by Taylor expansion converge quadratically, meaning that xk plus 1 minus x star is equal to, let's see, f double prime, or I should say not exactly equal, it's approximation, over 2f prime at x star times xk minus x star squared. So this is saying that the error after k plus 1 iterations is roughly equal to the error after k iterations squared times this factor here, and And this, the absolute value of it, f double prime at the root over 2f prime at the root, is the asymptotic error constant. So it's a constant proportionality between the new error and the square of a previous error. But that only works if, naturally, f prime is non-zero at the root. So, in other words, if f of x has a double root or triple root or a root of multiplicity greater than 1 at x star, quadratic convergence is not going to happen. So convergence would be linear in that case. So actually, so one of the problems in the book, I don't recall if I assigned it, it's showing, it can be proven that if f has a double root at x star but not a triple root, so just multiplicity exactly 2, you get linear convergence, and the asymptotic error constant turns out to be 1/2. So in other words, the new error is roughly equal to 1/2 times the previous error to the first power. In other words, the error is getting cut in half from one iteration to the next, which is pretty slow convergence. So method of bisection, which is something I covered last semester, that also converges by halving the error, and it's quite slow. So this rapid convergence only happens in this situation. Okay. All right. Oh, actually, I guess I could take this part. Okay. Let's see. All right. So we have that for the convergence. Okay. Convergence is linear. Okay. Now, another pitfall of Newton's method is that in many cases, not always, the initial guess x0 must be chosen sufficiently close to the root. All right, so unlike other methods, bisection, fixed point iteration, in those cases, you can guarantee convergence under certain assumptions as long as the initial guess is chosen within a particular interval, and the interval doesn't even have to be small. Bisection is any interval on which a function changes sign. For fixed point, it's any interval that the function g can map into itself and has a derivative that's sufficiently small. And you guarantee convergence for any initial guess chosen in an interval. Newton's method, most times you cannot do that. Unless you have certain really nice conditions, like on whether, like, the first derivative is only one sign, the second derivative is only one sign. In those cases, it is possible to prove convergence on a large interval, but otherwise, not possible. So we have to be very careful about that. One of my favorite examples involving Newton's method. Okay. If we have f of x is equal to a minus 1 over x, where a is some positive constant, then we have the following: xk plus 1 minus is equal to xk. Actually, it turns out to be equal to 2xk minus a xk squared. And this is what you get from taking the formula for Newton's method, this formula right here, and simplifying as much as you can. Because f prime is 1 over x squared. But you're dividing by f prime, so you end up multiplying by x squared. And that simplifies to this. Note that the root is x star is equal to 1 over a. So solving this equation, setting f of x equals 0, you're computing a reciprocal of a without performing any divisions. So it's a way of dividing without dividing. And this was used to implement division on certain IBM computers way back in the 60s in hardware, instead of a division circuit. Okay. Now, this iteration diverges unless the initial guess is chosen to be strictly, well, you want to be strictly positive anyway because you know your solution is positive. And it must be less than 2 over a. So, because otherwise what will happen is, if you choose x naught to still be positive but greater or equal to 2 over a, then what will happen is the new iterate will be negative. So you end up going to the wrong part of the graph of f of x. Okay. So one example why I had to be careful about choosing the initial guess, because that's pretty restrictive. All right. Now, drawback of another drawback of Newton's method requires evaluating f and f prime. So even though the iteration may be rapidly convergent, so you might not need many iterations, but each iteration can be expensive. What if f prime is a particularly complicated function? So an alternative is this iteration that looks very similar. So I'll have f of xk, and then, whereas before I was dividing by f prime of xk, what I will do instead is divide by an approximate derivative instead of the exact derivative. So now what I have here, this is an approximation of 1 over f prime at xk using a backward difference. So I'm using information from a previous iteration. This is the secant method. So then xk plus 1 is the x-intercept of the secant line connecting these 2 points. Whoops. Okay. Xk minus 1, f of xk minus 1, and same for xk. Okay. So now, keep in mind that f of xk minus 1, that was evaluated during a previous iteration. So there's only one new evaluation of f each iteration, and no f prime needed. So So on a per iteration basis, the work needed by secant method is less. The convergence is superlinear. So in this case, we have xk plus 1 minus x star. So a new error is approximately some asymptotic error constant, which I won't bother stating here, times the old error, not squared, but raised to the power p, where p is equal to 1 plus the square root of 5 over 2. So roughly 1.618. That's known as a golden ratio you may recognize. So it's still rapidly convergent, more so than many other methods. It's not as convergent, not as rapidly convergent as Newton's method, where the power is 2, but with each iteration being cheaper than that of Newton's, it's possible that the overall amount of time, computation time, might be less. And because you don't need f prime, the secant method is one that's often favored in real applications. Okay. So the reason why I'm reviewing these methods now is because how do we solve a system of nonlinear equations? So we have a vector valued function. All right, so now we have a function of several variables, and we want to find values of x, which is now a vector valued quantity. So f maps Rn into Rn. So we're trying to find values of the n components that gives us the zero vector in n dimensions. So we need to generalize these methods I've been talking about. So fixed point iteration, Newton's method, and secant to systems. One method I did not cover from Chapter 10 that was covered last semester, bisection, I've mentioned a little bit. That one I'm not bothering with. It doesn't really generalize well to a multivariable case. So we're going to skip over that. But these other methods can be generalized. And that's something I'm going to deal with on Wednesday. Okay. And then we'll be using those to solve certain systems of differential equations, or also boundary value problems that lead to a system of that's system of linear nonlinear equations in that case. Okay, but I just want to review where these methods come from and what their behavior is to try to carry that over to systems. Okay. Now, since we have some time left, does anyone have any homework questions? Yes.
I don't really have a homework question. I've always wondered, why do we always see the golden ratio come up with so many different things?
Okay. I would say, like in this case, if I were to go through the derivation of this convergence of secant method, where it comes about is so first it involves showing a relationship between the errors, and I think it's something I can show you. Oh, yes, I can. Okay. It can be shown that the new error is proportional to the product of the previous two. So now, if you imagine a what we just keep in mind that where the gold ratio naturally rises is from the Fibonacci numbers, each one being a sum of a previous two. And so the quadratic equation that leads to generate a formula for Fibonacci numbers, one of the roots of the quadratic equation is a golden ratio. And in this case, since we have a product of a previous two, but then when you have if you express each of these as something raised to a power, then you have a situation of exponents being a sum of previous two exponents. So there's a Fibonacci-ish thing going on there kind of behind the scenes. And because so really any kind of phenomenon where you have something being a sum of a previous two, that gold ratio is going to come up. So that quadratic equation, which is this one, that's something that must be lurking in there for that to happen. But yeah, it's kind of freaky.
Yeah.
3, 4, 3. Okay. Okay.
So I looked up that function.
Oh yeah.
When I looked at the example, they had to define a vector first and use the vector as a input statement or argument for that function.
Oh wait. Okay, which function are you talking about?
In the hint, you said we should use DI.
Oh yeah.
So I checked that on
Yeah.
the page and it wasn't really much help.
Oh. Okay. Oh, okay. All right. So for this matrix, all right. So to handle the minus twos, you have minus 2 times identity, and then for each of these diagonals, so this is an n by n matrix. Each of these two diagonals of above and below the ones on them is going to be, each diagonal is a vector of size n minus 1, or length n minus 1. So what you should do is create a vector of ones using a ones function of length n minus 1 for whatever n is. And then diag, so if you use diag, there's two ways to use diag, passing a vector or a matrix. So you're passing that vector of ones as a first argument to diag. And then the second argument to diag indicates which diagonal you want to place it on. So it'll be +1 for the super diagonal and -1 for the subdiagonal.
So what of the main diagonal at -2?
Well, for that you could create a vector of n ones and put it there and multiply the whole thing by -2. Or you could just do -2 times EYE for identity matrix. So you can add all these together.
So we're creating the sub-diagonal matrix separate, super diagonal.
Yeah, you create 3 matrices to count for each of the 3 diagonals and add them together.
And instead we're doing that for powers of, that's another finance, like powers of 2 to 10.
Just to select sizes to work with, because you're trying to see how the condition number behaves as a function of the size of a matrix. And I was just giving some suggestions on how to choose n. Because if you're choosing n to be something like if I just didn't say anything about how to choose n, somebody might choose something like 3, 4, or 5. It's not very interesting, but using powers of something, so you have widely ranging magnitudes in the size, then you get more interesting data, more informative data as to how the condition number is behaving. So you can set n equal to like 10 squared, 10 cubed, 10 to the 4, for instance. So then you'd have some fairly large, but not unreasonably large matrices to work with. And I think I want to check something here. Okay, yeah. So if you want to use something like powers of 10, then, yeah, if you want to do 3 examples, then you can have a loop that'll run 3 times over the exponent p. And then inside the loop, you set n based on n equal 10 to the p for that value of p.
So, like, how many A's are we creating?
I figured 3 would be enough. Yeah. Yeah. So really, what you're doing is you're making a vector of okay. So you can make a vector of n's, and then a vector of condition numbers that go with those n's, and then that is what you pass to log to plot. So setting each one like that for the condition numbers. Any further questions?
Can you please explain 3, 3?
3, 3, 8. Okay. Yeah. So the thing to use here is okay. Okay. Because we want to show that Y transpose A inverse Y is greater than 0 for any non-zero Y, given that X transpose A X is 0 for any non-zero X. Okay. Okay. Now, so what you can do is use the fact that because A is invertible, for any Y.
We're not proving that A is invertible.
Oh, no, you're not proving that.
Yeah.
Yeah.
A is non-singular. Are we proving A? Non-singular means it's invertible.
It's actually already been discussed that because A is symmetric positive definite, therefore if it's a positive determinant, it will be invertible. So yeah, you can just go with that. Okay. Okay. All right. Now, so because A is invertible, for any y equals 0, there exists an x such that y is equal to ax. Because x would therefore be A inverse y, which we know exists. So you can use that to try to get this because of this. All right, so try that and see how that goes. All right. What? Oh, okay, let's see. Wait, when do you have class?
I'll be here from 11 to 15.
Oh, right. Oh, wait.
Between 12:15 and 1 I'm free.
Yeah, go ahead and come by then,
Okay.
between the classes.
Okay.
All right.